Welcome to video number 2 in unit number 1. In this video, we're going to look at how atoms undergo transformations to become ions, and so that they can bond and create compounds with other types of atoms. Let's begin by defining what an ion is. An ion is an atom that has lost or gained electrons from its most outer shell, or in other words, its valence shell, and it can lose one or more. And we'll look at some reasons why it may want to do that in just a few moments. So an ion is different from an isotope because in an isotope we're looking at different numbers of neutrons all being a part of the composition of a particular type of element, whereas here we're looking solely at some changes that can happen in the most outer shell, leaving the nucleus intact. So if an atom loses an electron or electrons, and now we'll have more protons overall than electrons. And because it will have more protons and electrons, it will have an overall positive charge when you compare the number of positives to negatives. So ions that have a positive charge are called cations. And a really great way to remember this is that the word cation has a letter T in it, and the T looks like a positive sign. Similarly, if an atom gains electrons, it will now have more electrons than protons. So it will now have more negatives in its composition than positives, and therefore it will have an overall negative charge. Negative ions are called anions. So let's take a look from a Bohr-Rutherford standpoint how ions formed. And we're going to look at two scenarios. We're going to look at scenarios where metal types of elements, those on the left side of the staircase, become ions, and then we'll also look at nonmetals too. So looking at metals, we're going to begin today with a very small element on the periodic table. We're going to look at lithium. Lithium has an atomic number of 3 and a rounded atomic mass of 7. And from a practice we've done last week, we know that we can draw a Bohr-Rutherford model of this atom using this information. We know that its atomic number 3 tells us the number of protons and also the number of electrons that it has. So we fill 1, 2, and 3. Taking the atomic mass and subtracting the atomic number, we discover that there are 4 neutrons then in an atom of lithium, or at least in the most abundant isotope. Now, the premise behind ion formation is this. We want to zoom in our focus here on this outer shell. And when we look at the outer shell right here, we want to ask ourselves, okay, outer shell, what can we do to make you happy? And happy in the chemistry world means what can we do to make you full? We know that that second energy level can hold 8 electrons altogether. Right now, it currently has 1. So if we were a lithium atom, we would have to scrounge and find and look for 7 more electrons to fill the outer shell. That's an awful lot of work. And plus, what kind of force on the inside would hold them there? We only have 3 protons. So another alternative that lithium can undergo is it could, instead of gaining 7 electrons to get a shell, it could say, well, what if I lost this electron here in the outer shell? And now I would have an outer shell that is completely full because I know that this energy level here can hold 2 electrons, and lo and behold, it has 2. So if you were lithium, what would you do? Would you search for 7 or lose 1? The simple answer is you would lose 1. Now, if you take a look at the number of positives that you have in this structure, you have 3 of them. You have 3 protons in the center. But because an electron has gone, you now only have 2 negatives in this structure. We know that a positive and negative cancel each other out. And so we can see that overall there is now 1 more positive than there are negatives. So when we go to the Lewis symbol for this, we are going to let lithium's center be represented by Li. And to show that it has an overall charge of a positive, we're going to write 1 plus. Notice that this is a little bit different than what you're used to writing in math class, where you write the symbol plus or minus first, followed by the number. When we look at ion charges, we write the number first, followed by its charge. Let's look at another example of how metals, things that are on the left side of the periodic table, like to lose electrons to become positively charged. Let's look at something that's a little bit bigger. Let's look at aluminum. Aluminum is element number 13, and its average atomic mass, when rounded to the nearest whole number, is 27. from this, we can deduce that there are 13 protons in an aluminum atom, and there would also be 13 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So let's zoom our attention into this most outer layer. We see right now that it has 3 electrons. We know that in order to be happy or full, that outer layer, especially the third one, holds 8. So we have 2 choices here. We could either gain 5 electrons to make 8, or we could lose 3 to expose the full shell that's underneath. Well, the option that takes the least amount of effort, of course, would be for aluminum to lose its 3. So we take 1, 2, and 3 away. So when we look at this structure now, we see that there are 13 positives. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And there are now only 10 negatives because 3 of them left. And so we notice that the positive and negative charges cancel each other out, except that we now have residually or left over 3 positive charges. And by the way, there would be 14 neutrons in here too. I forgot to mention that at the beginning. But when we're looking at ion charges, we don't have to worry about the number of neutrons being in our focus. So how can we represent this as a Lewis structure symbol instead? Well, we can put Al, and if it had just been the element aluminum, we learned last week that we would have done this and shown the outer shell as having 3 electrons. But let's remember that those 3 electrons have left. So now we have the structure that you see as a Bohr-Rutherford model, and in order to show that it's not neutral anymore, we'll write in sort of superscript or exponent format the number 3 followed by a plus sign to show that it has a charge of 3 plus overall. So let's remember that the only charges that can leave the atom are negatives. They can come and go, positives always stay. And that's how metal cations are formed. Let's also look at how nonmetals or anions are formed. So nonmetals, of course, are those elements that are on the right side of the staircase of the periodic table, whereas our metals are on the left side. For a couple of examples, I'd like to begin, first off, with oxygen. Oxygen is element number 8, and its rounded atomic mass is 16. That tells us that there are 8 protons, and 16 minus 8 would be 8 neutrons. And of course, in a neutral atom of oxygen, there would be 8 electrons. 1, 2, 3, 4, 5, 6, 7, and 8. So let's examine this outer shell. And we see right now that there are 6 electrons in that outer shell. That outer shell, the second energy level, can hold a maximum of 8. So oxygen has 2 choices. It could either lose all 6 of those electrons that are present to expose this full shell underneath, which is going to be tough because those 8 protons are holding them in, or it could gain 2 electrons, losing 6 or gaining 8. Well, I would say that gaining 2 is probably a whole lot easier than losing 6. So let's add in then 2 more electrons. And just to show that these are ones that are being added in, I'm just going to do a different color, but they're still all the same particle. I just want it to stand out for you a little bit more. So there we go. A full outer shell exists now. Let's do a count of how many positives and negatives there are. There are 1, 2, 3, 4, 5, 6, 7, 8 positives. And because we've gained 2 electrons, we had 8 before, adding 2 more will give us 10. Notice that the positive and negative charges all cancel out, but we have an excess of 2 negative charges. So how can we communicate this using Lewis symbols, which is so much easier than using Bohr-Rutherford? Well, we can use the symbol O to represent the basic inner structure of that oxygen, but now we need to show that it has gained 2 electrons, so it's not the same as atomic oxygen anymore. To show that it has gained 2 negatives, we say that it has gained 2 negatives, or has a charge of 2 negative overall. Let's do one more example. Let's take something a little bit larger, and let's look at chlorine. Chlorine is element number 17, and its rounded atomic mass is 35. We'll focus on the most abundant isotope. there would be 17 protons, and 35 minus 17, 18 neutrons, and we would have 17 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Again, let's examine that outer shell. The outer shell has 7 electrons as we've drawn it. And remember, a full outer shell for the third energy level is 8. So it could either gain an electron to be full on the outside, or we could lose all 7 of those around the outside to show the full second energy level underneath it. So I think to myself, gee, gaining an electron or losing 7, I think I'll gain 1. That seems a whole lot easier than losing 7. So let's gain an electron. And if we do a count of our positives and negatives, we would see that we have 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17 positive charges from the protons on the inside, but we had 17 negatives before. We've now gained 1 more. There it is. There's an excess of 1 electron. So how can we write this using a Lewis symbol instead? Well, we can use the symbol chlorine, and to show that this is not just plain old chlorine, elemental chlorine, where we would have done this, showing that the outer shell has 7, it now has 8, but of course every ion would always have a full outer shell. The Lewis symbols would all look quite similar. So instead, we're just going to show the difference in charges that results of the gain of that electron. And so because it has 1 more negative than it did before, we can use the symbol 1 negative.